Assalamualaikum and a very good day to everyone. Today our group 6 from section 1 will be presenting our project on the design and simulation of a flash separation system for an ethane propane mixture. In this video, I will be walking you through the fundamental background, that is process overview, core assumptions of our system before passing it to my teammates. In the chemical industry, particularly in natural gas processing and petrochemistry, flashing is a vital auxiliary process. It allows us to efficiently split light hydrocarbon streams into basic vapor and liquid fractions before they undergo further high purity distillation. Because this is a single equilibrium stage distillation process, we assume that the vapor stream leaving the top and the liquid stream leaving the bottom are in thermodynamic equilibrium. This allows us to use standard vapor-liquid equilibrium relationship to predict the concentration of ethane and propane in both exiting phases. Our flash separation system operates at a controlled temperature of 64.4 degrees Celsius, which is equivalent to 337.55 Kelvin. The operating pressure inside the drum is set to 41.8 bar or 4180 kilopascals. Our feed is perfectly equimolar, meaning the inlet composition has an equal fraction of 0.5 for both ethane and propane. To calculate exactly how much vapor and liquid we get, we first need to find the pure saturation pressures using the Antoine equation shown here on slide 5. The formula is expressed as the base 10 logarithm of P sat equals constant A minus B divided by temperature plus C.
For the calculation, we are using a baseline of 1 mole of total feed with an equimolar split, meaning for our mixture is exactly 50% of ethane and 50% of propane. First, we find our pure component properties using the Antoine equation. At our system temperature, the ethane is highly volatile with a saturation pressure of 7,555.5 kPa, while the heavier propane sits at 2,246.2 kPa. By applying the Raoult's law, we find our upper phase boundary, the bubble point pressure. If our system hits 4,900.86 kPa, the very first bubble of vapor will form. Next, we calculate our lower boundary, the dew point pressure, which comes out 3,462.88 kPa. This represents the exact point where an all-vapor mix starts to condense. This brings us to a crucial checkpoint. Our actual operating pressure is set at 4,180 kPa. Because 4,180 kPa fall squarely between our dew and bubble pressure, we have a mathematical proof that our system is sitting inside the two-phase region. We have a physical mix of liquid and vapor. To see how components split, we look at our equilibrium K values. The ethane gives us a K value of 1.8075, meaning it strongly prefers the vapor phase. The propane sits at 0.5374, meaning that it prefers to stay at liquid phase. Now, for the ultimate question, exactly how much of vapor and liquid do we get? By setting a VLE mass balance, we generate the quadratic equation shown on the left. Solving of our vapor fraction give us a two mathematical roots. We discard the trivial root of 1, leaving us a physical vapor fraction of 0.4618 moles. By subtracting this in our 1 mole feed, our remaining liquid amount is 0.5382 moles.
This slide presents the calculation of the vapor and liquid mole fraction using the flash calculation method. First, the vapor mole fraction were calculated using the vapor composition equation derived from the Rashford-Rice flash calculation. For ethane, the calculated vapor mole fraction is 0.6583, while for propane, it is 0.3417. Next, the liquid mole fraction were determined using the phase equilibrium relationship. The calculated liquid mole fraction are 0.3642 for ethane and 0.6358 for propane. From this result, we can observe that ethane is more concentrated in the vapor phase, whereas propane is more concentrated in the liquid phase. This behavior is expected because ethane is more volatile than propane. To verify the accuracy of the flash calculation result, a material balance check was performed. The sum of the vapor mole fraction was calculated by adding the mole fraction of ethane and propane in the vapor phase. So then, we substitute the value obtained before and get the answer is 1. Since the total vapor mole fraction equals to 1, the material balance requirement is satisfied. This confirms that the calculated vapor composition are consistent and physically valid. This table shows the summary of the flash separation result. The feed entering the flash drum is 1 mole. After separation, 0.4618 mole is obtained as a vapor and 0.5382 mole as a liquid. The result demonstrates the effectiveness of the flash separation process in splitting the feed into two equilibrium phases. This table shows the composition of ethane and propane in both the liquid and vapor phase after equilibrium is reached. For the liquid phase, ethane has a mole fraction 0.3642, while propane has a higher mole fraction of 0.6358. In the vapor phase, ethane has a mole fraction 0.6583, whereas propane has a lower mole fraction of 0.3417.
From the discussion part, we know that the fresh separator produces 0.4618 mole vapor and 0.5382 mole liquid from a 1 mole feed basis. Then the vapor phase was enriched with the ethene 65.83%, while the liquid phase was enriched with propane 63.58%. Ethene also preferably vapor due to its higher volatility and vapor pressure compared to propane. The overall and component material balance was satisfied, confirming the accuracy of the calculation. Last, the result demonstrates that the fresh separator successfully achieved partial separation of the ethene-propane mixture based on differences in volatility. In the conclusion, a single-step fresh separation on an equimolar ethane-propane mixture was successfully analyzed. The process successfully produced a two-phase mixture at a temperature of 64.4 degrees Celsius and a pressure of 41.8 bar. The process generated 46.18% vapor and 53.82% liquid product. Ethene was concentrated in the vapor stream with 65.83%, while propane was concentrated in liquid stream with 63.58%. The material balance verification was successfully certified, confirming the accuracy and consistency of the phase separation calculations.